So we were down here. And again, I know this stuff to y'all seems like it's not a big deal, but well, if you're a conspiracy believer like me and Jessica, I don't know why I said Jessica, Julie.
Jessica. No, there's Lord.
Don't know why I said that.
This is my Lord. This is my Lord.
So was that a compliment or a?
I get called Jessica like more than.
I've taught 1,200 kids. Names get mixed up. Don't mean anything by it. Just there's so many names in my head. But if you're conspiracy theorists like us, well, you think the world might be destroyed and somebody's going to start over. So that's why you learn this stuff. So you can start all over again.
Yes.
Because there won't be calculators. Well, then you got to try to pass my class, huh? Okay, plain and simple. So find the linearization of f of x equals the cosine of x at pi over 2 and use it to approximate the cosine of 1.75 without a calculator. Now, the reason you're doing that is because pi over 2 is really close to 1.75. That's why they're centering at pi over 2. It is close to it, isn't it? Pi is 3.14 over 2. Right, so that's like 1.67 is a decimal. So it's really close. That's why they're centering there. Now, I'm going to write down the linearization formula again. Linearization of some x value is f of a plus f prime of a times x minus a. And they write stuff like this. I wish they would just say a equals pi over 2. Because that's where the center is. That is a. All right. Now your job is to do this stuff without a calculator. That's your job. I know I'm going to need to find f prime. I may as well find it, which isn't hard. F prime of x, what's the derivative of cosine? Negative sine. Now, we're going to find f prime of a by plugging in pi over 2, which you can do without a calculator. You guys memorized the unit circle. I know you did. What's sine at pi over 2? What's the sine of pi over 2? 1. So this would become a negative 1. Right? All right. And we need f of a too. Well, that's the cosine of pi over 2, which happens to be 0. And we just start plugging in numbers here. So we have 0 plus a negative 1 times x minus a. Now I know the a part's the pi over 2. What's the x part? It's the 1.75. X is that 1.75 part. So we are doing the linearization of 1.75 on this one. It's kind of funny they say without a calculator. But I guess we can just kind of use pi. I mean, everybody knows pi is 3.14, right? So we're going to figure out what 3.14 over 2 is. I think I already told you guys what it was. 3 divided by 2 is a half. 0.14 divided by 2 is 0.07. I think I actually said it wrong. I think it's a 1.67. It's a 1.57. So this would be negative 1 times 1.75 minus 1.57. And 1.75 minus 1.57 is what? 0.18? So negative 0.18 is my estimate, my approximation. Let's see how close I was. Because if I'm too far off, I screwed up. So I went back to radian modes, cosine 1.75, negative 0.178. Pretty close, huh? Yeah, not a big deal to y'all. It's really not. It's a big deal when you're trying to get to the moon. It was. If you think we went to the moon, right? All right. Now, the example one we did is actually a special case of a property that we're about to talk down here below. It's a special case of a general linearization formula that applies to powers of 1 plus x for small values of x. So the linearization, how's this one go? Of 1 plus x to the k is 1 plus kx. I think that's right. Do it. Yeah. I'm trying to look up one and see if we kind of did that. Yeah, we really didn't. So this is actually just some stuff in there like binomial theorem. Do you guys remember doing binomial theorem last year? No, you didn't do Pascal's triangle and dual enrollment?
That sounds kind of familiar, but it's interesting.
Binomial theorem is where you write out like 2x plus 3y to the 12th power really, really quick. No? Really? You don't remember binomial theorem? 2x plus 3y to the 12th is 2x to the 12th, 3y to the 0, plus 2x to the 11th, 3y to the 1st. You went through a pre-calc class, you didn't learn binomial theorem. Plus 2x to the 10th, 3y squared. There's a little more to it. There's a number in front of here too.
How is this quick?
It's quicker than writing it 12 times and foiling and triple distributing and quadruple distributing and quintuple distributing and sextuple distributing and what's 7? 7 tupling? In the end, you end up with something with 11 terms times something times like another 10 terms. Believe me, it's quick. Okay, well, anyways, you have any idea what that's talking about, so let's just follow the formula and not worry about it. So we're supposed to write the linearization of these things. This is the cubic root of 1 minus x. So I would view that as a 1/3 power. And just kind of follow the formula for the linearization. It goes 1 plus kx. All you got to do is identify the k pieces. This is your k. Right? Where's it go? In front of the x. So the linearization here would be 1 minus 1/3 x. It's really not a hard thing to do. The hard part is actually doing the rewrite. How do you rewrite 1 over 1 minus x? That's 1 minus x to the negative first power. So your linearization would be 1 plus x. Because we're doing a negative 1 times a negative x. Yeah, let's just jump to D. Actually, let's do C. I would write that as 1 plus 5x to the fourth raised to what power? To the what? 1/2. And then follow your linearization rule. Where's the 1/2 go? In front of the 5, right? So 5/2. Linearization of x is 1 plus 5/2 x to the fourth power. Don't overthink this. Like, don't do something wrong and think you give the half to both the pieces. Don't overthink it. And that's that guy. That's really about all you need to talk about that guy with. Now here is how they used to evaluate roots. Approximations of roots. Square root of 123 and the cubic root of 123. To do this, you still got to have a little bit of number sense. That's still got to be there, which, you know, back in the 40s, 50s, and prior, they had. I'm trying to find a copy that I haven't written on that doesn't bleed through, because we've got a lot of bleed through here. I don't seem to have a spare copy. Anyways, when you look at the square root of 123, what do you think it's close to? Huh? A little bit of 11. No. This is close to square root of 121. That's what it's close to, right? And Trevor said the answer should be a little bit more than 11 when everything's said and done. So that's kind of what we're going to center around. We're going to center around, emphasis on the A and around, A equals 121. Do our linearization. And it is a linearization. It's not the previous slide we just did with those linearization formulas. It just goes back to the first example. Linearization of x is f of a minus f prime of a times x minus a. It's point slope formula. That's all it is. So we're going to have to take some derivatives. We do have to write this thing out as a function before we take its derivative. Yeah, I guess you could just kind of take its derivative and worry about it being numbers. I don't know. But this is just the square root of some number x, right? Right? That's all it is. It's the square root of x. And that's what I'll use when I take my derivatives. So I know that f of x is the root of x. What would the derivative of the root of x be? Are you guys still going a long way? Okay. So that's 1/2 x to the negative 1/2. Two roots of x. Try and get where you can just look at it and do that. You know, after you do this a couple dozen times, you ought to be able to jump right to that. You introduce a half, the radical gets shifted down low. That's really all there is to it. You know, it takes longer to do it this way, but okay. There's your derivative. Now we're going to plug our 11 in, our 121 in there. F of 121 is the root of 121, which is 11. F prime of 121 is 1 over 2 roots of 121, which is 1 over 2 times 11, which is 1 over 22. That's all you need for this thing. Now the actual x value we're using here is 123. Doing the linearization or the approximation of 123. Notice how the x's line up. It is f of a, which we found to be 11, minus the slope, or the derivative when you plug an 11 in, 1/22, and 123 minus 121. So linearization of 123 is 11. What's 123 minus 121? 2, right? 11 minus, why am I using a minus? There's a plus sign in there. It's plus, not minus. Plus 2/22, which is 11 plus 1/11. I always tell kids to remember what calculators tell them. I don't guess you guys know what 1 over 11 is as a decimal, do you? No? It's 0.09 for all of eternity. That's what it is. You know, 50, 60 years ago, they did the long division. And because they did long division, they remembered what the decimals were. They used their brain to remember those things, because they did it quite often.
Why did you change the number?
What's 123 minus 121? 2. Anyways, this is 11.09 for all of eternity. Now, how close is that to the real thing? The actual root of 123 is that. So it's really, really ridiculously close. So there was one of them. Let's do another one. The other one is the cubed root of 123. The very first thing you have to do is you have to decide what you want A to be. What is something close to 123 that you can take the cubic root of? Of course it can be over. It's 5. I got lots of white space over here. I'll use this white space. Example B. Cubic root of 123. We let A be 125 because the cubic root of 125 is 5. It's close. That's what matters. Now, this is the cubic root of x, which I guess y'all are still writing like this, x to the 1/3. We are going to need its derivative, right? We will. F prime would be 1/3 x to the negative 2/3 power. Personally, I would do a rewrite on this, but I'm still a little more old school than you are. That's 1 over 3x to the 2/3 power. And I'm going to do this in my head. The goal is don't use a what? That's the goal. Try not to use calculator. I get that y'all have to because you grew up with one. But 1 over 3, if you remember your rule about exponents, you were taking the cubic root of x and then you were turning around and squaring it. So somebody just a little bit older than you would be looking at the derivative like that. I have no idea what they're teaching in college now, but that's what they taught us. Look at it like that. All right, so we already know a couple of things. F of A is the cubic root of 125, which is 5. I need to know F prime of A, which is 1 over 3 cubic roots of 125 that I square. Right? What's the cubic root of that 125? When you square it, what do you get? That's 1 over 3 25s, which is 1 over 75. Now, I think I've got everything. I'm going to write down the linearization formula again because that helps. Linearization is F of A plus F prime of A. The reason I want to do a minus here is because I'm accustomed to point slope where the F of A is on the other side. That's kind of why I'm doing that. Times X minus A. All right. What do we replace F of A with? 5. How about f prime of a? 1/75. That's right. What's our x value? It's the number you were actually curious about in the first place. The number you were curious about in the first place. So we're finding the linearization of 123, the approximation of 123. So here I have 123 minus 125. Now, when I do the cubic root of 123, I do expect it to be a little less than 5, don't I? I need a minus sign there, don't I? So this is going to force that negativity. 123 minus 125 is a negative 2. So this is 5 minus 2/75. I do not know what the decimal for 75th power is. Let me see if I can get at it another way. 5/75 is 300, 450, 448 over 75. No, I'm still not going to get there. That is the actual answer. I guess I'll approximate it with the calculator. It's like 4.97 with a 3 forever. Yeah. 1 over 75 is, okay. Now your actual answer, oops. What's that? 4.97318. Again, it's ridiculously close. Remember, you couldn't win World War II, or at least we would have won World War II. You couldn't nuke Japan without estimations.
So what if we don't pick the closest number?
Well, then you're going to be farther off. Well, you just don't have a very good approximation. Your estimate is only as good as your guess. That's the reality of it. It's only as good as your guess. So
You always need to compare your answer, your approximation.
I would compare it to, yes, what the actual thing is, just to see how close you are. Because like if you did like, I don't know, 216, which is 6 cubed, you're going to be off by quite a bit. So yeah, pick something close. It does rely on having a little bit of number sense, which, you know, previous generation had. And some of y'all still have some number sense. By and large, kids with number sense are the ones that are good at math. This is Newton's method. Newton didn't have a TI-84 in front of him. He couldn't look at a graph and use the intersect feature. Couldn't do it. The intersect feature actually uses Newton's method. But Newton could answer any equation. He could tell you where it crosses the x-axis by using calculus. And here's his method. It's x to the n plus 1 equals x to the n minus f of x to the n over f of x, f prime of x to the n. Okay, what you need to understand herein is that x to the n is your first guess. X to the n plus 1 is the result, and it's called the next guess. Because you do this thing until you hone in on an answer. And it will. It might take a couple of iterations, but this formula will hone in on an answer. It will. Now I'm going to run through one cycle by hand, and then I'm going to let the calculator do it because the fractions just get way too god-awful for me to do. Now, it's actually, that I may not even make it through a full cycle. We'll just see. Where do you think that equation crosses the x-axis? Because it's going to find it. Newton's method will find it. You just make a guess. Doesn't even have to be a good one. You're a jerk. Okay. There's a reason I'm saying you're a jerk. So he's guessing that x to the n is 4. That's his first guess. Yeah, there's a reason you're a jerk, because I'm going to probably have to use a calculator a lot quicker than I anticipated. Because I'm going to be cubing that 4. Stuff like that. And I'm going to have to cube its result. And there, it gets to be a long cycle when you do this by hand. But anyways, we have a guess, and I can't even write today. The guess is x equals 4. Now, Newton's method requires you to know the derivative. It does. Now, f of x is the original equation, x cubed plus 3x plus 1. F prime of x would be 3x squared plus 3. If you look at Newton's method, it tells you what to do. It says take your first guess and subtract f of that guess divided by f prime of that guess. You guys see that's what the formula says? Elizabeth, you see that's what the formula says? Okay. So our next guess, this x to the n plus 1, I'm going to call this first guess x0. x0 is 4. So the next guess x1 would be this 4 minus f of 4, a 4 cubed, plus a 3 times a 4 plus a 1, sitting over 3 times a 4 squared plus 3. 4 cubed is 64, plus 12 is 76, plus 1 is 77. So this is 4 minus 77 sitting over the denominator here. 4 squared 16, 3 of those makes 48, 51. That's 204 minus 77, which is 23. 104. This is 127 over 51. That's the next guess. The second guess is going to be 127 over 51 minus 127 over 51 cubed plus 3 times 127 over 51 plus 1 sitting over 3 times 127 over 51 squared plus 3. And I'm not going to be able to do that one in my head. You'll see. You hone in on it. What's going to happen is these numbers are going to get closer and closer and closer and closer together. So sadly, because a jerk chose 4, I don't even get to teach this thing the way it's meant to be done. But you guys are not going to do this, any of this in your head, are you? No, not a lick of it. So I was hoping you would choose an easier number, because then I could show you something like, has anybody ever taught you how to add sideways? What? I mean, add sideways. No, that's not what I mean. Like use some 4 and 5 digits and add them sideways instead of vertically. Okay, so anyways, you don't get to see that lesson because you picked the wrong stinking number. It's not. It's easier than adding vertically. You do not add 4 and 5 digits in your head. You don't add like a string of those in your head, do you? Don't lie to me and say you do. Yeah, it depends on the numbers. I can do 1,000 plus 3,000 plus 5,000 plus 6,000 all day long. Put a couple of digits after those things. So anyways, I got to figure out what this mess is. And instead of writing out this really complex string of things that I've got, I'm going to use a storage feature. So what I come up with X is 127 over 51. So I reckon I'll store that to X. 127 over 51 is that. You got to be really careful when typing this all in a calculator. The numerator is x to the third plus 3x plus 1. It's got to be wrapped. Divided by the denominator, which is 3x to the second plus 3. And I got that. If you look at my piece of paper, I was supposed to do 127 over 51, right? So x minus that guy is that. 0.798487179949. Amazingly, your calculator can convert that back to a fraction. It's kind of surprising. This ends up being negative 31 over 39. Let's see, we've gone from 4 to 127 over 51. We dropped quite a bit, didn't we? Now we're down to negative 31 over 39. It's still honing in. You see that? It's decreasing. It's decreasing by less, though. We'll stop once it's honed in. That's when we stop. You'll see that it's going to start getting really accurate pretty soon. Now, the number of iterations you do depends on how bad your first guess was, or how good your first guess was. Anyways, the next guess is going to be what happens when I plug in this negative 31/39. And I'm not going to write all this out. I'm just going to say minus f of x minus f of negative 31/39 over f prime of negative 31/39. I got a storage feature here. I'm also going to do this a little bit differently this time. Because the setup is to take that x value and subtract, and I'm going to store that to x, and I'm just going to write the setup. X minus x to the third plus 3x, crap, plus 3x plus 1 divided by 3x to the second plus 3. I got a negative 0.4094. Can't convert that to a fraction. Kind of got past the point of the calculator on that one. X to the fourth would be the same thing. Take that decimal, do all this math, okay? I'm going to restore that result to x, pull back up a previous operation, negative 0.32. This is actually the sixth guess at this point in time. It's called x5, but it's the sixth one. Stored x, second enter, negative 0.32. Well, of course we are, negative 3.222. Let's see what the next one is. It doesn't take that long to restore it. I'd say we're there. Within 4 decimal places, we're there. You see it? So negative 0.3222. Now, I'm going to make one up. It'll take me a second here. This one actually has two answers, by the way. We'll start this off by making a guess. So somebody make a guess. Okay, so the first guess is 7. Now, the setup here is going to be that the next guess is 7 minus the function itself sitting over its what? Derivative, f of 7 over f prime of 7. So you are going to have to figure out what f prime is, right? This is f. F prime would be 4x cubed minus 4x. Go from there. Now I want you guys to see if you can figure it out. No, just tell me what x1 is. Use the storage feature on your calculator. What are you going to store to x? Look, you little jerks, I can make you do it by hand. Because believe me, I could have done that last one by hand, but I'd probably only be on the third guess by now. Type in your calculator. What are you going to let x be? 7. Did I not show you how to do it? You store 7 into x. You type x minus parentheses x to the 4th minus 2x squared minus 1 sitting over parentheses 4x cubed minus 4x close parentheses. What'd you get? It jumped from 7 all the way to the negative 1? There are two answers, but it should not have jumped the y-axis. 5 point something? You got 5.282. Tanner, did you start off by storing a 7 into x? Parentheses maybe? 7 store x. Parentheses, do you have your derivative, your x to the 4th minus 2x squared up top? That'll do it. All right, now what do you do with that thing? I'm actually going to type this in. 7 minus parentheses x to the 4th minus 2x to the 2nd minus 1 sitting over 4x to the 3rd minus 4x. What do you do with that result? Store it, right? And I should have called that an x instead of 7. Second enter. Which gets me on to my next thing. Let me show you how to do this all in a calculator. So I'm going to start fresh here. I'm going to take a 7, store it to x. All right, that was my first guess. Now I'm going to type in x minus, you should probably play along with this. I'll write it out on a piece of paper. X to the 4th minus 2x to the 2nd minus 1 sitting pretty over 4x to the 3rd minus 4x. Hit the store key. Put the result in x. And what this does is this takes your 5.2872 and it puts it right in there. To find your second estimate, you press second enter. 4.0162. Huh?
You have to hit it twice.
You have to hit it twice. Second enter brings up the last operation. You press enter to perform it. You never use storage feature browser too, did you?
Oh, that's right.
See, I actually modified it. After this is all done, you go to storage. Anyways, I got a 4.016, and you can run through the iterations really quick. You know, this is the X, the third guess, fourth guess, fifth guess, sixth guess, seventh, 8, 9. Looks like it's going to take 10 iterations based on y'all picking that 4. Yeah, the 10th iteration gets you accurate to the 4th decimal. There's 2 answers though. You guessed a positive 7. Why not guess something negative? Negative 2. So let's take a negative 2, store it to X. Second enter. Second enter. This one won't take long. That's the 3rd iteration of Newton's method. 4th iteration. 5th iteration. Only took 5 iterations of that technique to get you to the right answer. Now, by the way, I knew it had 2 answers because I looked at the graph. You can use the graph to hone in on a point. You're still using Newton's methods. And when you do like the intersect feature, you know, you don't ever get your cursor perfectly on there, do you? It actually uses Newton's method. That's your first guess. And then it runs through Newton's method a couple times until it hones in on something where the decimal's been repeated 9, 10 times. Calculator uses Newton's method to figure that thing out. So it's not like you're not using Newton's method. You actually are. Well, that took a lot longer than I thought it would. I'm probably partially to blame for that. But this is how you do it quickly in a TI-84. You store something to X and then you type it in like that. And you press second enter, second enter, second enter, second enter.
Store whatever it is to X and then do it.
The very end of my function in my calculator, I put store X. That takes the result, puts it back in X. Do we need to do another one of those? Yeah, you just end it with store X. I have how long? Man, I hate it when lessons get spread out like this. This is a section called differentials, which are actually pretty important in calculus. So the differential for a function y, dy, is the derivative of the function times dx. Now the dx has been floating around there for quite some time. Dx literally means change in x. You kind of have to buy that when you see the word dx, that it means change in x. And we're going to find the differential dy and evaluate dy for the given value of x and dx. It's actually should be using the word estimate. What we're curious about when you look at a question like this is how much does the value of y change when you increment by 100th, but without actually plugging in numbers, okay, to some degree. It's called an estimation technique. So if I do A, what I would do is I would set this thing up And I ran out of time. dy is y prime dx. I guess we'll continue tomorrow.
Not coming forward. One question for yourself.
If you want to finish your test, you can.
Do you want to?
I'll grade them probably tonight.